Hi everyone, this is going to be a really quick video about simple and cyclic modules and a theorem that relates them. This is a standard result in looking at rings and modules, and let's go into defining simple and cyclic modules and then relating the two somehow. So let A be a ring over which we work. So we're going to consider all modules over A. Simple A module M, sometimes this is also called irreducible, has as its only submodules 0, I'll just say, 0, and all of M. So it has no non-trivial submodules other than itself, and I mean no submodules in general other than itself and 0. So it's somehow a building block or indecomposable in the sense of modules, in that there's nothing sitting within. It's the most atomic kind of module. Now we define a cyclic module. An A module is cyclic if there exists some element x in M such that M is equal to A times x. That is, it looks like all ring multiples of this one element x in the module where A is in the ring. Okay, so this is specifically for left A modules, and notice that I haven't really specified that A needs to be commutative, which it doesn't have to be, but we have to take some care in terms of defining left and right modules. The result holds for both because we don't lose any generality. Okay, so we want to prove a non-zero A module M is simple if and only if it is cyclic with what generator? Well, I claim that any non-zero element can be a generator. Any non-zero element as a generator. Great, so there's a really snappy characterization that ties cyclic to simple modules. That is, every simple module is exactly those modules that are cyclic, such that any non-zero element in that module is going to generate the whole thing. So it's cyclic with respect to any of its non-trivial elements. So the forward direction is almost trivial. Let M be simple over A. Then we want to show that any non-zero element x in M generates it. So x in M non-zero, which we choose arbitrarily. Then, however, x is a non-zero submodule because x itself is non-zero. Right, but then because the only submodules of M are 0 and M itself, and we know that everything generated by x is not 0, then everything generated by x must be just M. Hence, x generates all of them. It's that simple. Pun not intended. Okay, so this proves the forward direction because x was chosen without any meaningful properties. It's just random. Now, let M be cyclic with any non-zero element as its generator. Okay, we want to show that M has no non-trivial submodules. So now take N in M to be a non-zero submodule. And tacitly, our goal is to prove that if M has this property that it's cyclic with respect to any of its non-zero elements, then N is going to equal M. Sorry, bad handwriting. Great. Okay, we can pick, by assumption that N is not empty, some element X in N that is non-zero. And by assumption, since X is non-zero, it generates all of M. Thus, everything generated by X, since X is an element in the submodule N, everything generated by X must itself be a submodule of N. So N is contained in M because it's a submodule, but M is all of X. So we see that N and M get sandwiched in between these inclusions or equalities. And because X is contained in M, which is contained in M, which is equal to all of X, then we must have N equal to M so that M is simple. Great, and this proves the converse direction. So all in all, a fairly straightforward proof, I think. And now I'm going to give one exercise based on this that will examine the simplest case of cyclic or simple modules that you can consider, and that'll be over to the initial object in the category of rings or just the integers. So exercise. Determine all simple Z modules. Think about what a Z module is, tacitly think about abelian groups, and figure out what the condition is on an abelian group or Z module when you're considering it that way to be simple. And you can use this theorem as a stepping stone. So that's all for this video. Thank you for watching.